Well, hello everyone. Welcome back to Adrian's Digital Basement 2. So this video is a continuation of the Adrian After Dark video that I published recently about testing two Left 4 Dead Macintosh motherboards. One was a 128, one was a 512. Both of them had these RAM expansion boards on them called the Maximilian by Sophisticated Circuits. And in that first video, which I recommend you go watch first, I actually got one of the motherboards fully working. But the other motherboard here, this is a Mac 512, was originally a 512. Well, this thing is in pretty rough shape from a corrosion standpoint. And while it did power up, it always gave us a sad MAC code. So I figure there's something wrong with the RAM or something like that, but the problem is it's a little bit difficult to figure that out when you have a RAM expansion card like this. So I think in this video, I want to try to actually get this thing working. Now, I also stole the disk drive port because the one on the other motherboard, which is this one right here, was all rusty. So I stole it off this board, but I'm going to try to restore that because I have another Mac, which is this Macintosh SE right here. And it's a super drive model. This thing, as far as I'm aware, someone gave this to me. It had a battery blow up inside. So I think it's in pretty rough shape, but frankly, we need to open it up and take a look. So we'll do that in this video as well and see what the deal is with this thing. I mean, maybe the motherboard's actually fine. If the motherboard's fine on that, I actually have another dead Mac motherboard. It's a 2CI one where a battery also kind of blew up on that. And I could steal the DB19 connector off that to put back onto this motherboard. The other issue on both of these Left 4 Dead motherboards is that the headphone jack is very corroded and I don't think is really going to work very well. So I need to try to replace that. Now, hopefully the one on the Mac SE, if it does have a battery that went bad, is the same jack so I could steal that. But unfortunately, the headphone jack that's on the Mac 2CI, and I have another dead Mac 2 something or other motherboard, those are not the same connector. So I cannot steal those. These were the D-sub connectors I took off the Mac 128 motherboard, and I replaced the 9 pins from what I had in stock. They were brand new ones, but these 19 pins are not something that you can find anymore, hence the reason why I stole it from this board. Now, the rest of this board you can see is, well, it's not terrible, but there's this white stuff all over it, and this is like a hard water stain because it doesn't wash off. I've already given this motherboard a complete wash. The two ROM chips that were in here as well, well, they might be able to be cleaned up, but you could see that there's quite a bit of corrosion on there, and I have no idea if these work. When these are in the machine does nothing, and the only way I got this computer to do anything was when I inserted the ROMs from the other computer that worked into this motherboard, and then at least we got a sad Macintosh. Now, I wonder if something like CLR, which is like a calcium remover, would work on something like this. Is that safe to use on PCBs? If this motherboard actually can work, though, with just some contact cleaner in the sockets that are here, and this socket right here, which is how the RAM board connects up, and I would probably try to clean this connector up and put some Deoxit in there as well. If this thing can work, then maybe I don't really need to do too much more to it except try to replace the missing connector and then figure out what exactly is wrong with this RAM board. Now, it's missing a chip, but that chip is actually on the other machine because the other one was missing a RAM chip, so I stole it from this just temporarily. But it was even with a full population of RAM chips on here that we were getting that sad Mac when we turned this thing on. So I think the first thing I want to do is open up this Mac SE and see what's actually happening inside of this thing. It's really dirty. Look at the top here. That's pretty gross. This stuff on the side, I think it's sticker residue, so theoretically that should clean off. And on the back of the machine, the one thing that's interesting is there's no real evidence of any kind of leakage, at least that came out the back of the computer. Sometimes the leakage can be so bad that you actually see some corrosion that's sort of leaking out back here on the ports. We also have some type of a video board or expansion board in here. We have a 9-pin and a 15-pin connector. So I don't know if this is like a Radius full-page display card or what, but that's kind of cool. So hopefully the card that this goes to is actually in the machine, is attached to the motherboard, and is not too badly damaged if the battery did indeed leak. The camera recording my backup audio failed, so I'm going to narrate this section. The motherboard's not in terrible condition. Definitely the battery has leaked, but it looks like someone has tried to clean it up, and in the process, they also removed a bunch of parts from the board. It's not a big deal, though, because the parts we need are still on here. And this is awesome news as well. Looks like the headphone jack is the same component, and the one that's on the Mac SE, even though this metal plate is all rusted, the jack itself looks completely fine. For removing the floppy port, looks like we have rivets again, but you see how it looks like there is some solder, at least on that side, in the bottom of the rivet. And I think that's kind of confirmed by the fact that the rivet looks like it's filled in on this side, but not that side. I don't think that should affect us for drilling this out, though. Here's a close-up of the battery damage on this Mac SE motherboard. It doesn't actually look like it's, well, it looks bad, but I don't think it's completely too bad. It's probably fixable, but obviously the fact is a bunch of chips have already been removed from this board, so that means that it's not really feasible to fix this, and it's a perfectly good parts machine. Because we still do have good components besides those connectors on the back. Obviously, we have SIM sockets that actually don't look like they're broken at all, so that's good for fixing other things. And the stuff down here all looks good. CPU, this connector, stuff like that. So I'm going to spend a few minutes getting the floppy connector and the headphone jack off of this motherboard so that we can move on to trying to repair this one. The 19 pin has been harvested off the SE motherboard along with the headphone jack. And I got the headphone jack off the other motherboard, which was a lot more difficult actually because the corrosion there was kind of affecting the removal, making it a little bit more difficult. But the one from the 512 motherboard looks pretty horrible on the inside. I don't think I'm going to install this one onto this motherboard. I think this will go onto the 128 motherboard, and I'll just leave this off for now until I can find another compatible part to go onto here. I think next I want to remove and change out these two sockets for the ROMs on this motherboard because I just don't trust that these are going to work that well, especially with all this corrosion on the chips that were stuck into these two sockets. These two sockets and these two strips that were installed when the RAM card was put in are the better type, and I think these generally hold up a little bit better to corrosion. All I need to do is just scrub these really good and put some Deoxit in them and they should be fine. But these particular ones, these sockets where you can't even see the contacts, I really just don't like these. They get damaged very easily. All right, the sockets have been removed. Basically, the hardest pin was the power pin on both of these, or maybe it was the ground pin, that pin right there. So all you have to do is just do all the rest of the pins and then heat that one up as you try to remove the socket. And then you got to try to clear it. Looks like I got to clear that one a little bit better. But you can see all the corrosion that's made its way underneath here. And as I said, I mean, it kind of rubs away a little bit, but not very well. So let me try to clean this up a little bit, and then I'll reinstall some new sockets. The sockets are installed. I tried to clean up these sockets a little bit, the pins there, the connector as well. WD-40 seems to, well, clean up the motherboard a little bit and get rid of the hard water stains. I also kind of tested over here on the rusty parts, and that worked as well. I also took the two ROM chips and I put those under the polishing Dremel. I bent those two pins a little bit. So at least if the pins are making contact with the inside of the chip, they're gonna work. But this rust on here may have gone inside of that chip at least and rendered it inoperative. I think all the pins are straight, and there we go. And other than that rust right there, they don't look too bad at least. I'm gonna flood these sockets and this connector full of Deoxit just for best possible chance of it making good connection to the RAM board here. Make sure all the pins are straight. Uh-oh, I bent one. That's not good, because these bend or break very easily. Okay, hopefully that's okay. I'm just looking in here to make sure no wires are pinched. That one went in pretty easily. Okay, I think it's all inserted. I don't have the two screws in. I'll just put those over there for safekeeping. And before powering this up, just need to put a RAM chip in here. So I just have this one that I previously tested before. I suppose for good measure, I should probably reseat these as well, but you know what? Let's just try it first. See if these ROMs even work. I'm suspicious that these ROMs are not gonna work. All right, here we go, moment of truth. 3, 2, 1. No, okay. So this is what it was doing before with the two ROMs, the original two ROMs in this machine. It just was not working at all. So I'm gonna take the ones from the other motherboard here that works, and we'll do it one by one. That way we can kind of try to isolate which of these is bad. All right, so the right ROM from the working motherboard is in here. Oh, we're getting a different error now. Okay, before we were getting like 2800 or something like that. I think this error though, that starts with a 01, is a ROM checksum error. So the system is obviously getting a little further, but I'm just gonna put a dot on the one that I took out of the board that we think is suspicious. So it has a dot there. I'll put a dot on this one so I don't mix them up. So I'll take out the other one that I think might not be good, and we'll swap over the one from the other motherboard. All right, the left ROM has been swapped over. Turn this on. All right, 2.8. So from my reading, a 0.1 is a ROM checksum error, and 0.2 is a RAM error. That's what I can determine so far. And I guess what that means is that both of these chips are bad. One of them is so bad that it makes the system not work at all, and the other one must have some bit problems, so when it goes to do a ROM checksum, it then fails. So it seems like all the work that I did with cleaning the sockets and swapping out the ROM sockets and whatnot didn't really make a difference. We're exactly back where we were before, where this board is working as well as it did when I first tried it once I swapped over the ROMs from the working system. Now, as I just mentioned, the 0.2 SADMAC has something to do with a RAM test failure. And let's go read the document that I found that might help us identify which chip is actually bad. So on the Tinker Different forums, about to say Think Different, there's a post from 2022. I think this seems like this is information that was pulled from various places. And here we go right here on the original ROM, so the Mac 128 through the Plus. This is part of the Bootstrap ROM, has a RAM test in it, and this is what generates these codes. So the first two characters are the class code. The class code tells you what part of the diagnostic program found the error. The second four are the subcode. The subclass code tells you where the error was. In the case of a bad RAM chip, the subclass identifies the bad RAM chip, and this is very helpful for homegrown upgraders. So there we go, as I mentioned, class code 1, so 0.1, is a ROM test, and then the subcode is meaningless. So that has to do with a checksum. And I actually looked at a Mac Plus disassembled ROM. It was partially disassembled, and I could see it doing a ROM checksum there. Now, obviously, the ROM checksum is stored inside the ROM, so if your ROMs are having trouble reading, well, there's a good chance the checksum is going to fail, because whatever's stored in ROM, if it tries to read the checksum out of ROM and that's wrong, it's going to fail as well. And then the next four tests, 2, 4, 5, and 6, are different types of memory tests. So bus subtest would probably be address bus. And then test 3 is a byte write. So that's a write and a read from the RAM. That's going to check for bad bits inside the RAM itself. And then mod 3 is probably some kind of calculation that tries to look for adjacent bad bits. And then address uniqueness, which I think might have to do with a page error. So if writing to one memory location overwrites a different part of RAM. Then the next 4 digits are the chip identification. Now, of course, we have a RAM expansion card on here, but let's just imagine we only have the 16 chips that are built into the motherboard. So we have 16 data bits on this machine because it's a 68,000 processor, so data bits 0 through 15. And the bad bit is indicated by the 4 digits. Now, looking at the SADMAC code we have, it's 02, so that's a memory test, address test error, and then 8000 is the next 4 digits. Where if we scroll down, we can tell right here, 8000 is data bit 15. So the chip on the motherboard is actually G12. We actually have the chip on the motherboard that could be the problem, and we also have 3 other chips that are on the RAM expansion board here that are also a candidate for being bad. Now think about this logically. The 16 chips that are on the motherboard, each one of these chips is only 1 bit wide. So each one of them is connected to 1 data bit on the processor. And that's why there's a direct map telling us like data bit 15, which is the 16th data bit on this processor, is connected to a very specific chip. But when we look up at this board, it's a very similar RAM configuration where we actually have additional amounts of memory in 512K increments in banks of 16 chips. So it's just like the 16 chips on the motherboard, but it's replicated 1, 2, and 3 times on this board. So that means that this particular bad bit could be in the chip on the motherboard that identifies as G11, but it also could be on whichever chips on here are also connected to data bit 15. Let's do a little poking around with the continuity mode on the multimeter to see where we have connections between the various chips. So I'm pretty sure that pin 2 is a data bit pin on these particular RAM chips. And I'm thinking if we go, for instance, I'm just going to pick this chip randomly on pin 2, that these 2 chips are probably going to be on the same data bit. And that means there's going to be continuity on that pin. And there is there, and there is there as well. But if I go to the chip adjacent to it, there's no continuity on that pin. Now I'm going to make an assumption that whoever laid out this board probably did it as 0, 1, 2, 3 all the way through 15, or it could be the other way around where that's 0 through 15. So just to help me out, I've gone ahead and installed a chip clip onto that chip right there. And let's just make sure we have the data bus connection. Yes, we do. So these 3 chips are going to be all connected together. And now what I can do is I can flip this over. Let me get this power connector off of here. And I could try to figure out if this is data bit 0 or data bit 15. Now, looking at the web page, which I know you can't see it right now, it said it's G12 is data bit 15. And there's 12 right there. And where's the G? G is the bottom row. So this chip right here is data bit 15. Oh yeah, look, we have continuity. So that tells us right there that this chip, this chip, this chip, and the one on the motherboard, that is G12, and I touch it again, there we go, is data bit 15. So that wasn't hard at all to actually figure that out, and that tells us that the fault probably lies with one of these 3 chips or the one on the motherboard. I'm going to make an assumption that it's one of these chips on the card first. So we'll turn the system on. Let's just make sure we still have that same fault. Yep, it looks like we still do, so nothing has changed. That's good. And one by one, I'll just swap out the chips until we figure out which one is the problem. So I have a new one in the board there. Let's turn this on. Nope, I think we're still unhappy. Wow, we're not even getting anything here. Now, remember on that other Mac, oh, look. Okay. So we do have another chip that is faulty, but the RAM test on the Mac is not very good. And remember on the other Mac when it was working, there was an entire chip that was just missing from the board, and yet the system actually booted up and it got to the question mark just like that, but with a black background. Notice there's a couple lines in the disk icon, and we also have, well, no background pattern either. And that seems to be indicative of additional RAM problems that the system didn't detect. Just for fun, I'm going to remove the other 2 chips that are on that data bit that it complained about, and we'll just replace those as well, just in case. Okay, those are changed out. Let's turn this on. No, it's not better. So my assumption is that there's something going on probably in this top bank right here, because the top bank, yeah, it looks exactly the same. So those 2 chips are actually fine. So the only bad one is this first one that I took out, and I drew a little dot on it. Remember how I mentioned that the video memory, or what you see on screen, is up at the top of memory? I kind of have a feeling that this top bank of RAM here maybe is used for the display. And for whatever reason, the RAM test is not detecting a problem. And the reason why I think that, let's take out this random chip here. There's like one chip that was different on this board already. And it's this one right here. And I didn't even notice how horrible and corroded this looked. So this one was changed by someone else before me. And if we turn this computer on without that chip in place, I think the computer won't even detect that there's a missing chip. Yeah, it's like behaving the same. And that's sort of like the other motherboard. Yep, there we go. And it's very much like the other motherboard. When that chip was removed and missing, it didn't seem to care. It just gave us, well, it gave us a flashing disk, but it didn't have any of the gray background. And it's sort of doing what this is doing, although this is worse because it's got that line in it. So I'm going to put in a known or another chip here, a good chip, one from my little thing here. And let's see if that makes a difference. No. So I went ahead and I reinstalled this 19-pin connector, plugged in the external floppy drive, and let's see if this thing boots. That's what we're trying to figure out, right? Does it actually boot at all? Is it able to try to boot even? So let's see what happens here. I'm not holding out hope, to be honest. I mean, even though, oh, what? Okay, well, it started booting. We have a happy Mac, but the computer is dead in the water, unfortunately. The light turned off on the floppy drive after it booted for a little bit, and we're stuck there with that particular icon. What about the interrupt button? That doesn't do anything at all. And the reset button, I'm sure, yep, that reboots. If we had a speaker hooked up, we would hear the beep or bong or whatever you want to call it. Well, this is definitely some type of a RAM issue, right? It's got to be what we're dealing with here. And I'm back. And it's actually Adrian After Dark again because, well, it's late at night and I'm working on the Mac again. So I decided to take a break from working on this Mac because I felt that I was going down the wrong direction, or I wasn't really understanding how the computer worked. I was just sort of flailing around a little bit. At least that's what I felt like. So in the time that I took away from the machine, I sort of thought about the problems it was having, and then I thought about my tactics for getting this machine working. And I think the biggest thing I wanted to do was really start to understand how these old Macintoshes work. Now the Mac 128 and the 512 and the Plus are all basically the same machine, with the Plus just having some slight improvements. Namely, Apple simply added SIM slots to it for a capability of up to 4 megabytes of RAM and a built-in SCSI controller. But otherwise, they're basically the same. And I ended up learning that the Mac 512 Enhanced is really just a Mac 512 with Mac Plus ROMs stuck into the socket. It turns out the Mac Plus ROMs, when you put them into a 512, they fully work fine. They basically go and look for the SCSI controller, and if it doesn't find it, then it just, well, it says no SCSI controller, and it just kind of continues working. So that was a little tidbit that I actually didn't know. And what really led me to that conclusion was I found this spreadsheet after searching around, and unfortunately, I don't remember where I found this. So I'll put a link to the spreadsheet itself. But this goes over all the various Apple ROMs, because it actually has Apple II stuff on here as well. And here's the Macintosh Plus ROM from 1986, and notice it says Macintosh Plus and 512KE, or Enhanced. Now, it turned out there were actually 3 different versions of the Mac Plus ROMs, and the third version, V3, was the best one to use. I did some reading somewhere else, and it said that that particular ROM fixed some pretty bad bugs in those earlier ROMs, and really, you shouldn't use version 1 or 2 if that's what you have. Now, I personally was under the assumption that the 512 and the 128 had the same ROMs, but it seems like there's a different version that go into these machines. So there's actually a different checksum. Now, this spreadsheet right here says supported memory 128K and 512K for the different ROMs. I don't think that's actually true though, because I think it was pretty common back in the day to take your Mac 128 and swap out the 64K DRAM chips and put 256K DRAM chips in there, and you would end up with a 512K machine. And I'm pretty sure you didn't have to go swapping those ROMs, because Apple really wasn't in the business of selling just their ROM chips. They didn't want people to go and upgrade their machines. They would rather you take your 128K machine into the Apple dealer and have it upgraded to 512 there. And that would include the new ROMs and the RAM chips, and maybe they would just swap out the whole logic board. Yeah, it wasn't really a thing they wanted the consumer or end users to do, but I know that was something that actually a lot of people did do, because you could save a bunch of money doing that. So I have a feeling that these ROMs are pretty much identical, and maybe there's some slight revisions that changed. But I think what did actually change is the Mac Plus ROMs really did support up to 4 megabytes, as did the Mac 512K EROM, which of course is just a Mac Plus ROM. So yeah, that's why. So it's quite possible that if you had the original 128/512K ROM in your machine, and you have a RAM upgrade card like these motherboards have, that it might not actually work. You would just be capped out at 512K, and you would not be able to take advantage of the extra memory by adding these expansion cards. So learning about the fact that the Plus ROMs and the 512K ROMs are the same, that means that these ROMs that are installed in this machine here, the rusty ones that don't work, are actually Mac Plus ROMs. And the reason why that fact is important is I found some Mac 128K schematics, and that's what we're looking at right here. And unlike the Mac Plus schematics I had found, these are actually quite readable. They're not perfect because they're still scans of a handwritten thing and they're like photocopies or whatever, but they're still a whole lot better than those Mac Plus ones. Well, in taking a look at the ROM sockets that are on the Mac 128K motherboard, and of course the 512 motherboard since it's the same thing, I noticed by looking at the pinouts here, I noticed it's exactly the same as a 27C 256 EEPROM. And what's even more amusing is pin 1, which says not connected, is actually connected to address line 16. And that means you can use 27C 512 EEPROMs in this motherboard. It also means that these ROMs that were for the Mac Plus, which happen to be larger than the original ROMs, are drop-in replacements. So when Apple designed the motherboard, they clearly were thinking that, well, maybe they'd want to have some additional space for larger EEPROMs. Well, and that's exactly what ended up happening with these 512K ROMs, which are just Mac Plus ROMs. They just drop right in the motherboard. I think I mentioned in this video, or maybe the previous video on these machines, that I thought the ROM sockets were non-standard and I couldn't just use regular EEPROMs in them. Well, as I just mentioned, at least on the 512 and the 128, that is not the case, and you can just use standard EEPROMs to make new replacement ROMs for the machine. And that's what, and wow, it was glitching out there a little bit. I have no idea if that recorded. Anyhow, I went ahead and took the Mac Plus version 3 ROM, split it up into 2, and I made myself a couple EEPROMs, and we should try them out in this machine and see if they work. Now, I will add that on the Mac SE and later machines, I don't know about all of them, at least on the Mac SE, you cannot use EEPROMs. The pinout is non-standard, and you have to make an adapter or buy an adapter to use a replacement ROM. That happened because Apple wanted to keep the same number of pins for the ROM sockets, but they added extra address lines because the ROMs on the SE are double the size of these Mac Plus ROMs. I'm not going to cover how to make ROM chips for the Macintosh Plus, but there are plenty of guides online. If you just Google for it, you'll find lots of people talking about how to do it. You have to take a file you find online and then split it between either a high and a low or an odd and even byte, and then make 2 EEPROMs because it's a 16-bit system and these chips are 8 bits. And anyways, it will be explained in those guides you find online. All right, so with these ROMs in here, let's turn on the system. And I think we're just basically gonna have a working system. Well, as working as we had before, which is actually totally not working. And there we go, we're in exactly the same boat. If I put the disk in the drive, what do we get? We get a booting system that sort of doesn't boot all the way. Yeah, it just stops right there. So other than the fact that I've replaced the ROMs on this thing, we're still not in any better situation with this system working or not working. So there's something curious about what's happening when we turn this machine on, and also when we're getting that flashing disk question mark. We're getting those lines, those vertical lines visible in the graphics. And if we turn on the system here, we can take a look there. You saw those white bars? That's normal. That's just the RAM not being initialized on the RAM card here or on the motherboard. And those lines, though, I don't think should be there. And the reason why I say that is because now that the disk question mark is there, it has those lines in it as well. So I almost feel like this is a fault that's manifesting itself, and we're seeing it at that very initial turn on phase, which incidentally, if I take out one of the ROM chips, which will prevent the system from booting altogether, and we turn on the system, you'll notice here it's just sitting here stuck, which is completely expected, but we're seeing those repeating vertical lines. And I'm quite sure that when the flashing disk question mark comes up or the Happy Mac comes up, those lines are visible within that icon that's being drawn, which means there's something going on with the memory, which is used as a frame buffer, and it draws the image to the screen. And that's what we're looking at now. So in the break I took from working on this machine, I started really focusing on, well, the design of the system by reading the schematics and looking at how it all worked. So starting down here at the DRAM, now ignore the fact it says 64K because this is a 128K schematic, but it's going to be exactly the same. There's just one additional address line on 256K chips. Let's focus on the data line outputs from the chips. D0 through D7 and D8 through D15. It's only showing 2 chips, but it's actually talking about all 16 of the chips that are on the motherboard. An interesting fact about these old DRAM chips, these 1-bit, 64 kilobit, or 256 kilobit chips, is that they have 2 data line connections on them. On some system designs, one of the lines, pin 2, was used as like the input pin that was for writing to the chip, and then the output pin, which is pin 14, was used for the reading of the chip. So data lines 0 to 7 and 8 to 15, so on all 16 of the chips on the motherboard, actually make their way, and if we follow the trace here, the schematics are a bit hard to follow, they make their way all the way up to the regular data lines that are shared with, for instance, the ROMs, and they also go right to the CPU. Sorry, I just turned on my cursor highlighting. Hopefully it makes it a little easier to see the cursor. If we go back to the RAM chips, though, pin 14 is this RD 0 to 7 and RD 8 to 15. And that is a separate trace that goes to different things. For instance, it goes up here to the LS244s. And those 2 chips are on the RAM card here. And I actually thought that they were for address bus stuff, but they're not. They're for these RQ. I'm sorry, it was RQ. I thought it was RD. It's these RQ lines. I notice on the 2 buffers here, the line that enables the chip here is actually labeled RAM RD, as in RAM read. So it kind of implies that this RQ line is used for reading the contents of RAM. Now on the buffers, the input side is going to the DRAM chips, right? So that implies it's the output of the DRAM chip and it goes into these buffer chips. And then the output of these buffers, these Q pins here, are going to the standard data bus on the rest of the system. So it's kind of interesting to see that the RAM is connected to the CPU, both through those pin 2 connection, but also through these 244s. Now the 244s, which were on the motherboard, are lifted off the motherboard, plugged into the RAM card. But remember, those sockets that are on the RAM card have long pins, and it just goes straight back into the motherboard. And the reason why the designers of the RAM card wanted to do that is they wanted to make sure that they were able to connect all of the RAM chips on the RAM card to these same RQ lines that also go to the RAM chips on the motherboard right down here. Now you might also be wondering, well, how are they connecting to the data lines on the RAM card, right? Because the RAM chips on the Macintosh need to be connected to both the data lines like 0 through 7 or the RQ 0 to 7. Well, they can do that, of course, because on the RAM cards here, they have both sets of data lines, the regular D lines that go to the CPU and the RQ lines. So on the RAM card itself, they're connecting all the pin 2 of all these RAM chips to the D side here, and they're connecting the pin 14 to the RQ side. Now, I'd mentioned, I think in the first video, there's a set of pull-up resistors here, and I thought that it was picking up the data lines from those. But that's not actually the case when we look at the schematics. Here are those two resistor packs, the ones I was just pointing to, that are now installed on the RAM card. And what they did when they installed this RAM card is they removed those two resistor packs, they installed sockets, and there are pins now that go through the RAM card down into the motherboard, plug into these sockets, and then those resistor packs are installed up here. And you can see all the signals that are on here. It's all the address lines that go to the DRAM chips, along with the RAS and the CAS lines, or at least just the CAS lines, actually. As you can see, all the RAM chips on the motherboard use the same RAS line, and so do all the chips on the card. It's the CAS lines that you need to worry about, because the different CAS lines, you can see there's CAS 0, CAS 1. You can think of CAS lines as bank select registers. So the fact that there's only 2 CAS lines on the Mac 512 means that those additional CAS lines for these additional banks of memory that are on this card have to be generated by something. And that generation is happening by the PAL chip that's on this board. That's taking these 2 CAS signals and maybe a couple other signals off the motherboard, and then figuring out based on address lines that are coming from the CPU, it creates additional CAS lines to address those extra banks of memory. A system like the Mac Plus will have that logic on the motherboard in one of the PAL chips that Apple designed to allow up to 4 megabytes in those SIM slots. But yeah, in this older system, it really only supports 512 without some other logic to generate those additional CAS signals. Okay, so what does all this tell us? From best of my understanding, the pull-up resistors are required for the RAM to work at all. And we're talking even the motherboard RAM. So if there was a problem with the connection, like between the motherboard and the card, the system wouldn't run at all. It would just immediately crash and tell us there's a RAM error, like without fail. There's no way it would get past even the initial RAM test that's on here. Next, those 244s working are required for the system RAM check in the ROM to even be able to check the RAM at all. I don't think the system would pass any RAM checks because it looks like it's using those 244s to actually read the RAM back. Like for instance, if it writes to the RAM and then reads back, it needs those 244s working. So the fact that this system is working at all, even though it's not fully working, but it's sort of working, means that those chips gotta be okay. Now what's interesting is in my time away from making a video on this machine, I really was trying to study the schematics here, and I came across these 2 LS166s. These are underneath the RAM card, so we can't really look at them very easily. But as you can see, these are connected directly to the RAM chips on the RQ lines. And what these chips are serial shift registers. So they're parallel to serial shift registers. So these take parallel information coming from the RAM chips and serialize it. And these 2 chips are actually cascaded together. So pin 13 is the output of the shift register, and this one over here, which is RQ 0 to 7, output is actually fed back into the other one, and then its output says ser vid, as in serial video. So these 2 chips right here are essential for taking RAM stored in memory and then converting that to information that you can look at on your screen. And the interesting thing is, if you look at the width of the screen on the Macintosh, it's 512 pixels. Well, there's a very good reason for that. That is directly divisible by 16, as in 16 bits. And because we're using these 2 serial shift registers with all 16 data bits connected to them, really the block size of your screen increments, well, it needs to be in 16 pixel increments, and they just happen to have picked 512. Now, what signals drive these 2 shift registers are the PALs, and if you trace this serial video signal, it goes over to a PAL, and then what comes out of that is actually what goes to the connector, which goes to the monitor. The PALs are doing all the timing, generating like the horizontal vertical sync, and also strobing the address lines going to the RAM. So that 60 times a second, it's reading the contents of the screen memory and then displaying it via these shift registers. Now, we can learn a few things by looking at the schematics. RQ lines here are connected directly to the RAM chips. You see the trace trace here goes right down to the RAM chips. It does not go through the 244 buffers. So if there were a problem with the 244s, it would not affect what we're seeing on screen when it comes to what's in the RAM. And when we first turn on the power, the RAM is just initialized to that kind of like white and black pattern. And we're seeing those lines, and it's 100% consistent. I've noticed I can turn this machine on after being off for an hour, off for a minute. You're still gonna get that white and black big vertical lines, and then we have those repeating patterns in there. It's really gotta be telling us that we either have a bad LS166 shift register or we have a bad RAM chip. If you think about how the shift registers convert the data in the memory into display video, it's reading a bit from each one of these consecutively. I think it starts over here. It goes like 0, 1, 2, all the way through, and then it repeatedly does that. So for instance, if we have a bad RAM chip, say this D4 is bad, this is RQ4, then anytime the shift register goes to read that, it might just always get back a 0, and then that'll make a vertical line. Or I guess it's inverted. So if it reads back a 1 every single time, no matter what's stored in the contents of the chip, then we're gonna see a black vertical line. And that's kind of what we see. Even when it goes to draw like the disk icon or the Happy Mac, it has those black lines in it. Now, as I mentioned, it could easily be something wrong with the shift register itself, or it could be a problem with the RAM chips, right? Like we don't know which it is, and it could be either. Now, poking around a little bit more in the schematics also reveals that the RQ lines here are connected directly to the sound chips as well. So these are also serial shift registers, and it looks like the upper or most significant 8 bits of the RAM. So we're looking here from R15 all the way down to R8, and that again is connected directly to the same like read back pins on the RAM chips. And here it outputs this sound res. When I followed up to this section of the board here, where it's doing a little bit of shaping using op amps and stuff, and there's the headphone jack, and then that comes right out of the speaker output from the connector on the motherboard. This is why on a Macintosh, if you remove the RAM from the motherboard and you're trying to turn it on, you get both a lot of static on the screen and you get a bunch of weird noise like static on the speaker. That's because those data lines are just floating. And those shift registers, when they go to read back the contents of the RAM, because they're constantly doing that, they're just doing it all the time while the system is running, well, what's gonna happen is just gonna read back random garbage, and you just hear a bunch of like static and stuff like that, and you'll see it and also hear it. What I can do is we can take a speaker here, and I've connected it to the ground pin here on the connector, power connector, and I hooked it up to the middle pin on the headphone jack. Because the headphone jack is missing, it's not gonna route the audio through to the pin on here. And if we turn on the computer, we should hopefully hear a normal beep. Oh, the ROM's not installed. All right, the ROM's back in, turn this on. Okay, normal beep. So that means I guess at least the upper 8 bits of the RAM, the most significant bits, are working. Let's hit the reset button. I'm just listening to it. I mean, it's hard to know if that is missing a bit or has like some static in it that shouldn't be there because maybe one of the RAM chips is bad, but it seems to sound fine, at least like through this little speaker. So I've also been reading a little bit about the way the Macintosh memory map works. And when the system boots up, what happens on 68,000 computers is the ROM is overlaid on top of where the RAM is when you first power on the system. And that's because the 68,000 starts to boot from the very first address of memory, all zeros. So what happens is the ROM needs to be there so it can start executing code. But very quickly in the ROM on the Macintosh, and pretty much all 68,000 machines, Amiga's the same, it basically goes and controls one of the VIAs or the CIAs, depending on what's on the motherboard, to toggle that overlay off, which puts the ROM back in its normal location and then puts the RAM back at the beginning at the bottom of memory. And in this technical documentation I found for the Mac 128, it talks exactly about that. And it says normal memory map when overlay is 0. If overlay is 1, that means that the ROM is down at the bottom here. But in overlay 0, which is set very quickly once the system boots up, if you go look at the ROM code, very, very soon after power up, it switches over to overlay 0. And what happens is you get RAM at the very bottom of the address space. And this is for a Mac 128. I don't have a later version of this for like the Mac Plus, but it's gonna be the same. So what happens here is the memory starts at all zeros and there's only 128K. And what happens is the memory is mirrored. It's imaged over and over and over again, all the way up to the 4 megabyte boundary. And that's where the ROM starts. And then the ROM is also mirrored over and over again, 15 times here, all the way up to the next boundary. So that way, if you have a 64K ROM like on the original Mac 128 and 512, Once we upgrade to the larger ROMs of the Mac Plus, it just works because instead of 64K of ROM, we now have 128K of ROM. And there's plenty of address space there for that to fit into. And when Apple designed this memory map, they actually already allocated 4 megabytes of space between the RAM and the ROM boundary. So when you would add additional RAM to the system, it just totally can work. Now, this is actually one of the reasons why there's a hard limit of 4 megabytes on the Mac Plus and Mac SE and Mac Classic, because they all have the same memory map just like this. And the ROM is physically starting at the 4 meg boundary, so you cannot have RAM anywhere else. I mean, you can have RAM somewhere else, but typical OSs like the Mac OS here requires continuous RAM for operation. It can't use RAM that's somewhere else in the system, and that's very common. In fact, that's just like on the VIC-20. When you add extra RAM on the VIC-20, some of it can end up in other chunks of address space, and BASIC can't see it. It doesn't show up in BASIC, and while you can use it if you have a custom written program, the OS just doesn't know how to handle that because the OS needs continuous RAM so it can allocate and deallocate memory, as it needs it. Anyhow, so the RAM starts down here and it has a lot of extra space for RAM images. So normally that 128K is mirrored over and over again. If you have 512K of RAM, then essentially that 512K is also imaged over and over again, all just not 31 times. It will have 1/4 the images of that, all the way up to that 4 meg boundary. Now, a little further down in this document has a more detailed look at the memory layout of the actual RAM, right? So here's 0, and this is 1FFFF, which is the top of that 128K. Now, the important thing for us to see is that the screen video memory is right here, and there's a second page right here. So there are 2 pages in memory on the 128K Mac. We can also see that there is some disk PWM memory, and that has to do with like the speed of the disk drive, and then the sound buffers up here, and that seems to have 2 copies as well. And I think there's some other stuff like stuck in between this, like OS level things and whatever. But down here, this chunk right here between the bottom of this screen video memory page 2 and this bottom hardware stuff is where additional memory goes. Well, remember how I said when you add extra RAM, when you go from 128 to 512, it still mirrors that 512K over and over and over again? Well, what happens is when the OS goes to write to the screen memory, instead of writing to the actual screen memory, like say right here, this 01FC7F, it doesn't write to that. It writes to one of the mirrored copies that are much higher up in the memory space. And here's a disassembly of the ROM from the Mac Plus. That's the one that's actually in here right now. And here you'll see exactly what I'm talking about. So right here we have something that's calling this address 3FA700. And then it goes to a routine called erase screen buffer. What this is right here is the address of the screen memory. But notice it doesn't match what we saw in here, 01A700. It's 03FA700. And the reason why is that this code, the Mac Plus ROM, is writing to the mirrored copy of the screen memory. So on a 128K or a 512K Mac, when you have the Mac Plus ROM in there, it's still able to write to the screen. Instead of writing to where the screen is actually held in RAM, it's writing to one of the high-up copies, and there's a really good reason for that. The reason why is if you have a 512K machine, or say you have a 128K machine, and you stick these ROMs in it, what happens is when it goes to write to that upper screen memory, up at the top of the 4 megs of memory, well, that RAM doesn't really exist. But what does exist is a mirrored copy of the 128K over and over and over again. So when you write to that 3F whatever address we saw here in the code, it's actually writing into this page 1 memory right here. And that has a really cool side effect of allowing that stuff like the sound buffer and the screen memory to be always at the top of the physical RAM, but the OS itself and the ROM always just writes to that very top of RAM. So no matter how much memory you actually have, whether you have 512K, 1 meg, 2 megs, 4 megs, it doesn't matter. It's always able to write into that correct part of physical memory because of the way the mirroring happens. It's kind of a clever solution, actually, that allows the gap of free memory for programs to always exist in the middle of all of this stuff. So with my limited assembly knowledge, especially in 68,000, I was perusing through the disassembly here, and I found that in the check routine for the RAM, what it does is it quickly goes through and just tries to figure out where the RAM starts to repeat. Once it starts detecting those mirrors, it knows that's the top of memory, and then it sets that into one of the CPU registers, and then when the ROM starts to boot, it tells the OS, hey, I was able to detect 512K of RAM, so don't try to go above that because the RAM doesn't physically exist. But if it detects all 4 megs, it passes that off and says, hey, we have 4 megs of RAM, you can use that. Now, right here are the routines for the RAM test itself. And remember how I mentioned when you take out RAM chips in the higher part of memory on this board, it doesn't seem to detect that? Well, that's because the RAM check in here is extremely rudimentary. And from the best of my knowledge, I don't see it doing any kind of RAM checking in here other than the most simple RAM check where it's looking for addressing errors and specifically trying to find the top of memory. I don't see any kind of RAM check in here where it's actually trying to check to see if the RAM is good or not. And remember we looked at that one guide online, I forgot the link now, where it said like, you know, code 2 with a SAD Mac is an addressing error, but then there was like a 3 and a 4, and how I never got to see any of those on here, no matter what I did. If I pulled out chips and put bad RAM chips in, it just would never do it. That's because I don't see that in this code. The only thing I ever see this thing doing is a 01 SAD code for a ROM checksum. I do see that. I see a 02 for a bus or addressing error, and that's during that simple RAM check. And then I see a 0F, and that's if you push the interrupt button after the system is booted and it's waiting for you to insert a disk. That's the only SAD codes that I see whatsoever. In fact, this is the entire SAD section right here, and all this does is basically clears the screen, and then it draws the SAD I put a few things in here. There's the routine. It jumps to this. That draws the icon, which is stored in the ROM itself. And then what it does is, I know I wrote error code. This just is the position in screen memory where it's going to draw the error code, and the error code fonts are just right down here. This is how it gets like the little letters and numbers to display what the error is. And that's all it does. And at the very bottom, there's just a little tiny routine that just loops infinitely, and it draws those little dots that just sort of permanently will just look like static. That's it. It doesn't do any kind of RAM checking, doesn't do anything in there. It just simply takes a passed value to this routine, either 1, 2, or F, and then that's it. It just prints a few extra characters that are from a different register, and it just sits there indefinitely. So I think the whole idea of a more comprehensive RAM test on the Mac Plus and the earlier Macs, I don't think it's there. Unless someone can like go read this and figure out that there's more to it, I am 99% sure that it does not exist, which explains why fooling around with the RAM chips on this board never produced any additional RAM errors. But wait, there's more, and I figured out something else kind of interesting. If you look at this motherboard here, if we look at the motherboard, there's a wire that goes from this chip here, a 6522, and it goes to the RAM card. And I didn't really think about what that's doing. But now that we have the schematics, it's on pin 13. Let's look up pin 13 on the schematics. Here's a 6522, the VIA, and this does all sorts of stuff. It's handling the mouse, it's handling the keyboard, which has a microcontroller inside the keyboard itself. So it's handling all the keyboard data and clocking. It's also handling some floppy drive related stuff. In fact, it's funny because notice this pin 7, HD select, that's head select. So even though the original Mac had a single-sided disk drive, Apple 100% was ready for double-sided disk drives with the very first Mac in 1984, and that's what that signal is. It also handles all the clock stuff, but what it also handles on pin 13, if we zoom in a little bit, mouse switch. So when I go look where this goes, it goes to the mouse connector, and it is the mouse button. That is how the OS is able to read you holding down the mouse button or clicking the mouse button. So that tells us the RAM card is connected to the mouse signal, which means pressing the mouse button would have an effect on this card. So you might be asking, what exactly would they be doing with that? Well, the only thing I can think of is holding down the mouse button, which I have connected here, might disable the actual additional RAM. You might have a situation on an old Mac where a game doesn't work with extra RAM and you might want it off. So let's push the button, the mouse is plugged in, and let's turn on the switch. And look at that. The system freaking works. So with the RAM card disabled, it's working. Let's put in the disk here and see if it boots. Like, I don't know if this disk here is good for a 512K system, because I'm sure that's all this has right now. But this seems like it's doing more than it was doing before. I mean, yeah, the amount of seeking that we're hearing here, I don't recall it doing this when I had the RAM card enabled. So there we go. If you have a Maximilian card, now you know, hold down the mouse button when you turn on the computer, it disables the card. So it's a good way to test if the system is working. So we should have 512K of RAM here, I'm assuming. Yep, there we go, 512K. Okay, well, this is wild. This is telling us that this motherboard, which I thought was no way it was gonna work, does work. And also, as I explained, these 244s that are on here are completely essential for the OS to run, because while the video doesn't need them and the sound doesn't need them, the CPU does need them. And I'm sure if I pull one of these out, the system will not operate at all. Why don't we give that a try? There's a lot of wires here with the speaker sitting there. I'm gonna pop one of these out here. And what I'll do is I'll hold the mouse button down and we'll turn on the system, and I'm sure we will not get an operational computer. It will immediately crash. So we have an unhappy Mac, and we're getting that 02. So we're getting like a RAM address error. Remember, 2 is one of the valid ones. Now, I don't know why there's lines there though, because obviously this is not required for the video display. Obviously the numbers are fine and stuff like that. Probably what's happening is there's a routine in ROM that like writes the icon to RAM somewhere and then reads it back, and then that reading is not working, but the little unhappy face in the middle, which is probably, you know, the sad Mac face and the happy face is the same main icon with just the little face switched out. So that's probably the reading and writing not working. And because this chip is missing, we're getting those lines there, which are just floating data bus lines to the CPU, and the CPU is just reading that kind of as garbage. But of course, the RAM check is failing immediately as well, because this needs to be working for the RAM check to work. And popping that back in the system and holding down the button, the mouse button, notice that pattern looks totally different. And it also ejects the floppy disk. That's something the Mac Plus ROM does as well. And if we push the interrupt button now, we're gonna get code F. If we press the reset button now, look at that. So the RAM card is re-enabled again, and we got those lines. What I'm gonna do is I'm gonna hold the mouse button down and push the reset button. And we're back. Right. It seems that once the system is booted, it doesn't look at the mouse button anymore, and I have a feeling what's going on is one of the wires that comes to the PAL chip is probably going to that overlay signal. So as soon as the ROM code disables the ROM overlay, it's what I explained about the memory map, it probably stops the PAL on the RAM card from looking at the mouse button anymore. But when you hit reset, the overlay is turned on again, right? There we go. Which probably makes it look at the mouse button again. And without reverse engineering how this card works completely, I have a feeling when you hold the mouse button down, what it's doing is it's not generating those extra CAS lines, and that just makes this computer only see 512K of RAM, and it will affect the addressing as well. So that 512K that's on the motherboard just loops over and over and over again. So when the ROMs write that disk icon in the gray background to the RAM, it's going onto the motherboard RAM, and that's why there's no lines and it's totally working. But when you reboot without the mouse button held down, the extra CAS lines and the addressing is taking effect where this thing has 2 megs of RAM. So that means that 2 megabytes of RAM is mirrored just once. And when the ROM goes to write to that upper video RAM page, it's writing into, I guess, the top row of memory on this card. And it's just gotta be bad. There's just gotta be a bad RAM chip in this top row of memory. Like, I just don't see how it can't be anything else. Now it says row C, row B, and row A. My assumption is that this is the second 512K of RAM. So the motherboard's the first, then this, then this, then this. So let me summarize where I am right now. I know a lot more about what's going on with this motherboard. I still don't know why it's not working. Obviously it's working when I hold the mouse button down. So functionality of the Macintosh itself, perfect, working great. I just needed to switch the ROMs. I mean, that was literally the only problem with this one too. Totally amazing that these two motherboards work. And we just have some kind of a fault that's gotta be related to this RAM card, whether it's a bad connection, a bad socket, bad trace, or a bad chip. And unfortunately, without a better diagnostic ROM, I think there's really no way for me to kind of zero in on where the problem might exist. The fact the system mostly works, except for those vertical lines which are repeating on regular patterns, it's just gotta be a bad RAM chip, and it's sitting right in the buffer space of where the video memory is when the system actually has 2 megs of RAM. It's gotta be, it's just gotta be. And now really, it's just a matter of trying to figure out where exactly the bad chip is. So I'm probably gonna do a jump cut here when I just go and take these chips out one by one, deoxit the sockets and all that, and just try to figure it out. All right, I figured it out. Well, I haven't figured out exactly what's wrong, but I figured out how this is all working. You'll notice tons of chips are removed from the board here. And what I did is I brought up a SAD Mac with the lines in it, and I started pulling chips while the system was running. Because, you know, if I use this, I can just boop, pull them straight out. I pulled out most of the chips here, right? And the weird thing is it wasn't having any effect on the SAD Mac. No additional lines were appearing. And I'm sorry, that doesn't make sense. Pulling RAM chips when the system was running, and it hadn't crashed, by the way, because you know how the SAD Mac has little dots underneath it that kind of scroll through, and that's ROM code that runs. The RAM is not necessary for the ROM SAD Mac to work. The SAD Mac runs entirely out of the ROM code itself. So pulling the RAM out doesn't crash the computer. And nothing I was doing, I mean, I have almost all the RAM chips out, nothing. It didn't change anything. Well, the only explanation for that happening is that the memory on the motherboard is now the top of memory. So that this RAM card is the first, second, third bank, and the fourth bank, which is where the video memory is and the sound buffer, is what's on the motherboard. And holding down the mouse button doesn't disable the card and just use the motherboard. It must just make it where the card configures itself for 512K and it doesn't even use the motherboard RAM at all. And I have confirmed that that's the way that this card works. Check this out. What you can see right there is a SAD Mac that comes up when I hold down the mouse button. So if I power cycle the computer now without pressing the mouse, there it is. We saw the lines. It's exactly like it was doing before. It's crashing right away. But that's understandable. If the RAM on the motherboard is the top of memory space, well then the bottom of memory is all completely missing. The first 512K, the second, the third 512K is all screwed up and missing bits. But then what's on the motherboard, which is now mapped to the very top where the screen is there. And that's how we're able to see something. If we turn it off and hold the mouse button down, we don't get a proper beep at all. And we barely have any of the Mac. And if I switch to this view, I bet you this first bank, which currently has 3 chips in it, is what's displaying the screen there. And it's because it's reconfigured it where just this bank is all that's being used. And if I pull out this chip right here, we should lose one of those lines. Here we go. There we go. Confirmed. What this is telling us is that the bad RAM is on the freaking motherboard and it's not on this card at all. Oh, I was just assuming. I made the assumption that the way this card worked is the motherboard was the first 512K and the additional memory was what's on this card, not the other way around. That also explains why the RAM test is not able to detect bad RAM chips in the upper banks, because it doesn't seem to do that. That RAM test doesn't exist in the ROM. It only detects the most rudimentary issues in the first bank, first 512K, and that's it, at least on these ROMs. And that is also why when we go to boot the OS with all 2 megs enabled, it crashes. And that's because the onboard memory on the machine, which is the top part of memory, which is used for various registers and values or, you know, variables or whatever, is bad, has a bad bit. One of the bits is bad. So, if, you know, the manual for this card probably explained exactly how the whole memory map worked. Without that, you know, there was a whole lot of guessing, and it's impossible to know how this whole works without a bunch of reverse engineering work by just trial and error. And that's exactly what's going on right now. So yeah, now it makes sense. I mean, I was pulling chips out of the board and nothing was changing. And I'm like, how is that possible? It's not possible. Pulling chips out should cause lines to appear in the SAD Mac, and it wasn't. Oh. So I'm gonna take the rest of this RAM out of the board, and then I'm gonna put one of the other banks, like the top row, into the bottom row, and we'll see if that's working with the mouse button held down. And if that is, I'll reinstall all the RAM, and then I'll take this card off, and then I guess we'll have to try to figure out which chip is bad on the motherboard. There's no good RAM tests. Why is there no good RAM tests? We need a RAM test for these machines, and that would allow us to find the bad chip. All right, I have figured out how to figure out what is the bad RAM chip on the motherboard. Check this out. Now all the RAM is back in the RAM card. If we turn it on, we're back to where we were before. We have lines exactly like we had before. Now I'm gonna hold the mouse button down, I'm gonna hit the reset button, And what that's going to do is, there we go, system is working. That's because it is now using this first bank of RAM here for the 512K. The motherboard's not in play, nor is any of the other RAM. Now watch this. If I take out one of these chips while the system is running, okay, well, it crashed. But what I wanted to show is that it generates the lines. And that's because taking out the chip is, I guess, going high. And remember, the video signal is inverted, so a high signal is actually a 0 or black on what we're looking at here. But now the lines are in a different position. If I reboot the computer here without the mouse button, the video display memory on the motherboard is where the problem is. And you can see the left line is obscuring part of the 2, and it's just to the left of the little screen icon there. But if I hold the mouse button down and we power it on, the line is now over a little bit. And that's because I just pulled out a random chip. All I need to do is pull out the right chip on here that coincides with the line on the motherboard, and then hold the mouse button down, and that lets me confirm to see exactly which chip on the motherboard is freaking bad. And there we go. I think I figured it out. I have data bit 10 pulled out on this first bank here. And if we power up the computer without the mouse button, so this is the motherboard bad RAM, there we go. We have the line right next to the screen. And if I hold the button down, and actually I guess I can push reset, there we go. It's in exactly the same freaking place. So we know for sure, of the 16 chips on the motherboard, the one for data bit 10 is freaking bad. And if this thing just had any kind of decent RAM test, it would have been able to tell us that. That chip is completely dead, which is why we're getting a line. It's the same as me pulling it out of the motherboard. Like, if we could piggyback, it would probably make it work. But since you can't piggyback with this RAM card on here. So yeah, don't be under any illusions that the Mac Plus has any kind of good RAM test, because very clearly it has garbage for RAM test, like beyond garbage. So I'm gonna pop this card off, and I'm gonna cut that darn chip out of there and put a new one in. And then this machine hopefully is fixed. All right, the offending RAM chip has been replaced. And what's funny is when I was getting the old one out, one of the legs just sort of came off. And it wasn't just broken at the, well, where it goes into the body, the whole body just sort of cracked. You see that corner pin right there? Yeah, it didn't survive. So I don't know if that was already bad and that's why this failed. Maybe it was cracked and moisture got in there and that's what killed this chip, but whatever, it's dead now. Put it in the dead parts pile. New one is in with a socket, and yeah, remember it was data bit 10, so it starts over here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 over here. So let me reassemble the motherboard, and hopefully it's fixed. I also cleaned a little bit under here while I was at it. Alrighty, are we ready? Will this thing work? I'm not gonna hold the mouse button down. The speaker's hooked up, power. I mean, let's see what happens. No lines, no freaking lines. And now we're getting the diagonal pattern, which is awesome. Wow. You know, what's really weird actually is why when there was a bad RAM chip, the pattern didn't appear. I don't really get that. I'm not sure what goes on, what causes that exactly. But, I mean, but it speaks for itself. Let's put the disc in here. I mean, look, it's got a background. It has a pattern. It looks right. I can't believe it was a bad chip on the motherboard. I mean, I believe it. But what's amazing is I just thought, I was just like, no, it's got to be something on the card. It's got to be the card with the sockets, the soldered chips on the board. Can't possibly be the problem. And yet, once I finally understood the logic of how this thing all worked, let's see, will it be 2 megabytes? 2 megabytes! It freaking works. It finally freaking works. That was fun. I gotta say, these types of problems are kind of cool. I mean, it was a bit of a struggle. I really did have to pause, you know, after that first part of this video and just think through what was going on. And I'm really glad that I finally figured it out, that the memory on the motherboard is the top of the address space. It is the video buffer. It doesn't need to be that way. It could be the memory on here, on the board itself. That could also be the memory at the top of the address space. But for whatever reason, that's the way the designers of this board decided to do it. And I'm glad I figured that out finally. I mean, it didn't make sense removing the chips. How it wasn't affecting the video. So that was the light bulb that finally went off, and I was like, oh. And then when I figured out holding down the button, that was a good little trick. And then I was able to figure out which chip here caused the line in the same spot, which directly told me which chip on the motherboard it was. So yeah, I didn't have to try to get this thing working. I was originally thinking I had to try to get the motherboard working with the card removed, which would imply I have to reinstall that AS253 or whatever that chip is that's missing, and all those wires are soldered in there, and I have to desolder those and then put them back, and then that's just a nightmare. But I didn't need to do that in the end because I was able to use the button trick plus figuring out which line, which chip caused the line. So yeah, anyways, that is going to be it for the repair of these two Mac 512 motherboards with the Maximilian RAM expansion cards. And yeah, Adrian After Dark. What do you think about it? After Dark as in the screensaver for Macs. Kind of, punny. Maybe that's not a pun, but whatever. I like it nonetheless. So let me know what you think about this series here. This has been a second channel video. It's kind of like I would normally put this on the main channel, but I didn't really think that this little repair of these two motherboards would be as in-depth as it ended up being. But nonetheless, second channel deserves some good content too, and not just like mail call episodes or something, although people probably like those as well. And it's not super late. Oh, it's pretty late actually. I think I'm gonna go relax a little upstairs, watch a little TV, and then head to bed. So if you enjoyed this repair of these motherboards, I would appreciate a thumbs up. If you are surprised as I am that these things freaking work, yeah, I would appreciate that thumbs up. Put that comment down below as well. I didn't really summarize. What was wrong with this motherboard was 2 bad ROM chips, and we had 1 bad RAM chip on the motherboard, and I think at least 1 bad chip on the RAM card as well. And that was it. I mean, that's it. Both of these boards were like really, really reliable. I think the other one had, what, 1 missing RAM chip, and that was it? I think like nothing was wrong with that one. Just the ports, obviously, I had to switch. So anyways, absolutely fantastic and amazing that these motherboards are so freaking reliable. By the way, I didn't say, when I got these, they were just loose in a box of junk. Like they weren't stored in anti-static bags. They were just thrown in a box, which I guess if you're considering these were outdoors or wherever they were for as long as the whole machine, the rust around it, if they survived that, then they could survive being thrown around in a box too. And I mean, I've been manhandling these and they freaking work still. So anyhow, yeah, if you didn't like this stuff, you know what to do. Thanks to my patrons. Their names are scrolling beside the screen over here. They make it possible I do this full time. Thank you very much to them. And you can become a supporter at a link in the description below. And I think that's really going to be it. So stay healthy, stay safe. I'll see you next time. Bye.